Hello everyone, I am Akbar Rahmati Zive, a PhD student at Czech University of Life Sciences. In this video, I will introduce you evapoRe, an R-based application for exploratory data analysis of the evapotranspiration. Then we will go through some practical usage of the evapoRe. evapoRe is a toolbox and database for global evapotranspiration. It also provides multiple methods for potential evapotranspiration estimation. The software or the package, let's say the package is available in the Chrome. You can easily download the package and install it in R and use it. For our database, we did some pre-processing. Since all of the data were not in the NetSDF format, we convert them into the NetSDF format. Then we homogenize all of the data in terms of variable name, in terms of their measuring units, and also we remap all of the data in 0.25 degrees. So all of the data have the same spatial resolution. Then we store the data in public Zenodo to make it accessible for all people. This is our database. We have data from satellite-based hydrological model products and reanalysis-based products. We have data from 1948 to 2023, and if you are interested in any of them, you can easily call the function in evapoRe and download a single data or even all of them. As I mentioned earlier, we have some functionalities that you can calculate PET using those functions. We have different PET methods in our package, and from a very simple method which requires only T average, which is Heyman or Odin, to the most complex one in here, which requires more inputs, which is a Penman-Montes formula or Percy-Taylor, or even if you are interested in other formula, we have I would say wide variety of the method that you can use them. So in short, evapoRe is a package that you can download the data. You can validate in case you have your own observation. You can validate the global data sets with your observation, and through some plotting options, you can visualize some statistics of the evapotranspiration or actual evapotranspiration, and then analyze your maps, the visualization plots. These are some examples. I will go more in deep in the practical uses. These are some examples. With a single line of code, you can download a single data set or even the whole at once. This is an example of the PET method that you can use PET function to calculate a potential evapotranspiration. For example, in here, Odin, by using Odin method and providing average temperature, you can calculate potential evapotranspiration easily. We have also some drought indices functions that you can calculate drought indices, which is purely based on the evapotranspiration, actual evapotranspiration, and potential evapotranspiration. So in order to use these drought indices functions, you need to have actual evapotranspiration and potential evapotranspiration. So we have actual evapotranspiration from the global data set, and also we have potential evapotranspiration from our functions. So it is easy for the users that to use these functions in case they are interested. We have also some other functionalities like the extreme evaporation event detection, that you can use them to detect extreme evaporation. The idea behind the extreme evaporation event is from the Yanis Marconi's 2025. If you are interested in the definition, you can go and Google it and find about this idea to see what it is. And we have also some plotting options that you can use them through the evapoRe to plot your results. For time series analysis, we have time series analysis. We have we have some plotting option for density plot. We have for benchmarking. We have also this. We have also Taylor plot Taylor, which you can use it for validation if you are interested. So this is for now a brief introduction. We will go through the practical usage. So for the practical part, I suggest you to download the latest version of the evapoRe from the GitHub, then load the library. For downloading, you can download the data, the single data. You can download the single data, or you need to download the whole if you want. Let me show you how you can download a single data or the whole. Data name, it could be any of the dataset which already we have in the package. So from the list you can see that you can select any of the datasets. So let's select one of it. For example, FL-DAS. You need to specify the domain. Right now we have only the land domain, so no need. The default is land. We have a different time resolution from daily to the annual. For right now I just want to show you to download a simple dataset at the yearly, which takes less time. Then pass, you can define the pass. You can save the data in your project folder. For me right now, I'm interested to put it in data. Then you can easily download the data, and it will go through go into the data. So it's easy as it is. By a single function, you can download a single dataset or even the whole. If you run this, it will download the whole database. If you specify the variable, we have also have potential evapotranspiration. So if you specify the variable name to the PET, it only downloads the potential evapotranspiration. So let me show you how many. So for example, if you specify the PET, it will only download the Era 5, Gleam version 3 and 4, and as well as TerraClimate. If you don't specify, it will automatically download the actual evapotranspiration data. So this is how the downloading the download data works. You can see that for example, this is our naming convention. You can see that how we name the data. For example, you can see from here that FL-DAS is the name of the dataset, E is the variable, millimeter is the unit, and this is showing the domain, which is land here, and this is starting and ending point of the dataset, and this is also showing the spatial resolution as well as temporal resolution. So I already downloaded the data. So I already downloaded the data, and we also have ET from the FluxNet. Actually, we use the latent heat to ET function that calculate ET from the latent heat, and we calculated ET in each FluxNet sites, and then store it in our package, which serve as an observation in here. So you have ET in FluxNet sites. Then I extract the global data, global evapotranspiration data in these locations, and I compare them, compare global dataset with the FluxNet with the tailored diagram. You can see how it looks like. This is a seasonal Taylor diagram. So basically in here we have a wide variety of the evapotranspiration products from global sources, and we have observation from the flux net. If you're interested to see how different products is behaving in some range, latitude or longitude range, you can choose longitude range and latitude range from the plot Taylor function in the evapoRe, and to see, let's see, for example, this is annual, this from the whole data. Let's make it seasonal. And then, so now you will see how it looks like in some latitude range, latitude and longitude range. I mean, it's in a sample point. Basically in here we have less points, and the result are near to the flux net. The global ET estimation is near to the flux net data for the spring, mainly for the autumn. So so I already showed you how to evaluate the accuracy of evapotranspiration product with the FluxNet observations in the evapoRe using the plot Taylor. There are some other plotting options. So let's move on. I will show you a couple of them. I subset the data for the Mediterranean using the subset data from the TWC package, and also generated area average time series from the again from the TWC package. If you are interested, you can look at to the TWC package help page. And let's move on. Let's see how different evapotranspiration dataset behave in terms of annual evapotranspiration. You can look at to the time series, annual time series from the plot TS output, which is from evapoRe. Let's look closely. So you can see that the camel is in top, while it's GL Dasvik is in the below. Let's move on. There are some others. For example, the density plot from the evapoRe. Let's select some dataset and plot density plot from the for different datasets at a monthly scale. So this is showing how different dataset behaves in terms of monthly evapotranspiration over the Mediterranean region. This is generated from the area averaged monthly evapotranspiration. So this part is done almost. So let's move on for the next step. So we will look at to the so in this part we will focus on the PET calculation. For calculating PET using the evapoRe, you need to do some steps. First of all, you need to download data for the variable you need for each method. Let's say that, for example, I just want to calculate the PET. In here we will mainly focus on these two methods, Taylor and Pembermontes. So for this, let's see how many variables I need. For this, you need to look at to this. So for Pembermontes, you need average temperature, minimum temperature, maximum net radiation, wind speed, dew point temperature, elevation. For the Price-Taylor, you need average temperature as well as net radiation. So we store some of these data in our package. You can easily call the download EMV data and download these data from the evapoRe package, and then calculate PET. But before going to PET calculation, you need to calculate net radiation as well, since Price-Taylor needs net radiation as well as the Pemberton-Montes. Also, the wind speed that we have is in 10 meter elevation, so you need to convert it to the 2 meter wind speed at 2 meter, which you can use the calculate tool from the evapoRe and calculate wind speed at 2 meter. So the final step is to calculate the Pemberton-Montes PET. Then converting the unit from millimeter per day to the millimeter per month. Now we calculate the PET from Pemberton-Montes method. You can easily look at let's say for example, you can plot it. PET. You can look at the first layer. This is the PET for the Iberian Peninsula for different months, and yeah, so let's go to the next part. And so so now I will calculate also the PET from the Price-Taylor. Then I will show you in which dataset we have exceedance of the actual evapotranspiration from the potential evapotranspiration for different seasons through using a function from the evapoRe. So let's go and let's select some global datasets and subset them for the Iberian Peninsula. Then so with this function, so now we prepared AET with the PET data. Okay, let's look at the data. You have AET and AET and PET from Pemberton-Montes and Price-Taylor, AET from different datasets. So now I just want to show you how this plot AET exceedance will work in different months actually right now, and I will show you later on in different seasons. For months it will take too much time since it is heavy. This is calculating the exceedance frequency. The frequency of the pixel exceeds in which AET exceeds PET. So for example, looking at to the season winter winter season, you can see that for example the terra climate is exceeding in almost 50 or 60% of the pixels, the AET from the terraclimate is exceeding the PET from the Priester-Taylor. So it's kind of useful benchmarking to show that which dataset is working properly in terms of AET exceedance of the PET. Now, so let's move on to the drought part. For this, I will calculate PET using ODIM method, and I will get the actual evapotranspiration data from the ERA5. Then I will calculate the drought indices for year 2000 to 2020 for the Spain domain. We need average temperature for the Spain, which we have it. We already downloaded using the download DMV data. Then you can easily calculate the PT using the ODIM method, which requires only average temperature. You will provide it, and it will calculate the PET. For the AET, we have it already. We already downloaded. We downloaded the whole database, so you can easily crop it for the Spain domain. Then we merge these two data. The AET and PET into a single data table to calculate the ESI from the evapoRe using the calc ESI function. Then I just want to show the median for each months through the whole period from 2000 to 2020. So this is showing how the ESI look like over the Spain domain. Let me show. Okay, so now the higher values indicate wet period. The lower value indicate dry period. So let's do the same for the SAEDI. Again, we use the calc SAEDI from the evapoRe package to produce to calculate the SAEDI. Then we use the plot map from the evapoRe to plot the SAEDI map again, which is quite similar to the ESI. So let's move on to the next part, which is about the extreme evaporation analysis. So for this, we need daily evaporation data. We will download daily evaporation data from the Gleam version 4. Then we will crop it for the Mediterranean. For the Spain domain. So we already have the Gleam data in our. We already downloaded actually. So let's only use the crop data function from the TWC to crop the data for the Spain. The crop data is also from the TWC. So in TWC we have a couple of processing and C processing functions like crop data, subset data, and FLD min, which we use it in this tutorial, I would say. It will take a bit time since the daily data is really huge. It was almost 20 gigabyte. Now we are cropping it into the Spain domain, and we will only calculate the calculate the extreme evaporation for year 2001 to 2020. Then we will make it as a table with the tabular function, again from the TWC, which takes raster or NC data and convert it to the data table format. So we crop the data, we make it tabular, and we detect the extreme. Now let's look at a single pixel to see how extreme evaporation look like. The function is from the evapoRe. The plot exe ev is from the evapoRe. You can assign it and you can save it to see how it looks like. So this was the final part from the evapoRe usage. I hope you enjoyed. Thank you very much for seeing this video.